Welcome back. So, in the last class, we discussed inverse kinematics using analytical techniques. So, we did the inverse kinematics of 2R, 3R, SCARA and industrial serial robot. So, most of the tasks that you see in the industry, which are of pick and place type of task, when a robot can pick an object from a definite place or a pre-programmed place and it can put it to a particular location. So that type of task can be easily performed by just programming the robot from point to point, irrespective of the path that it follows. Okay, while going from point A to point B, it can follow any path. But there are quite a lot of applications when you need to continuously servo the robot. That means continuously robot is fed with a new position without having knowledge of next location. Okay, like for example, visual servoing. You are continuously putting in the robot with a new set of points and robot goes there. So can we do programming for these kinds of application also using inverse kinematics approach? Or there are few other approaches that we'll discuss in our today's class. So there are few terms which are to be known before you actually start with that. So today we'll be discussing on differential motion analysis, robot Jacobian, will do velocity analysis. So moving ahead. So yes, before we actually begin, let us just discuss on differential motion, what it is and mathematical definition of Jacobian. As such, Jacobian is a mathematical term. It has got not much to do with robotics. Robotics is just one of that application. So let us just start with Jacobian. So let us take a function of x, which is y, given by yi is equal to f of x1, x2, x3, and these are the input variables till xj. Got it? So this is your function. If you take partial derivative of y, you can quickly write it as y1 is the first output variable, yi is the ith variable, x1 to xj are the j input variables. So taking with respect to the first output variable, so you can write it like this. Next, going in a similar manner, you can directly write it like this. Okay, if you can pack it together in the matrix form, so the vector of delta y1, delta y2, 2, delta y3, delta y4 and so on till delta yi, y1 to yi are I different output variables. Okay, and this becomes your input variable vector. So it is delta x1, delta x2 till delta xj. So they are j input variable. So you see there is a pack of differentials which are there in the form of matrix. So this is a matrix which relates the input vector to the output vector and both are the rates. So rate of change of input variables comes here, rate of change of output variable that goes here. So this particular matrix basically relates the input rates to the output rates. Got it? So this is known as a mathematical Jacobian. In case of robotics, let us say it is a 6 degrees of freedom robot. So end effector position is a function of joint angles. In case of 6 degrees of freedom robot, it has 6 joint variables, theta 1 to theta 6, at least in case of revolute jointed robot. So it is like this. Output is a pose. So it is basically position and orientation. So what we are seeking here, these are the angular velocity rate of the end effector. These are linear velocities of the end effector. Okay. So this is the input joint angle rates. So input joint angle rates, this is the input and this is your output, and both are related by a term which is known as a robot Jacobian. So this is what we are looking for. This is very, very important. In case of robots, you see there are few applications that we have seen earlier also. I'll just repeat them once again. So you see this is an application when a robot is programmed to pick an object from a definite location and put it on the conveyor at a fixed location. You see, there are n number of robots, all can be programmed in a similar way. Got it? So this is a pick and place operation. There are many similar applications which you see, which finds similar programming technique. When you are not bothered about the intermediate points, you just are concerned with the picking spot and the placing spot. Got it? A similar one, you see it is here, when robot is picking an object from a fixed location and hanging it onto a moving conveyor. So these type of applications, they don't need any robot Jacobian in between. That may be required for the control purposes, but definitely not for the programming the path that is achieved in this type of task. This can be easily achieved using inverse kinematics based technique. When you know a location, you just find out the joint angles. You know the other location, you find out the joint angles. Take your joints from this to this without any collision in between, that you can verify while checking your program, by pre-running your program before actual execution. Okay, so that is one of the way that you can do those kind of tasks. Now let us see a different type of task. Okay, so this is a welding task, you see. So it is continuously, robot is continuously moving along a path and it deposits the weld. Okay, it continuously moves. Got it? So what you see here is the robot continuously deposited the material. If at all it has moved with different velocity in between, a lump of material will be deposited in a particular place. So while moving along the path, it has to move with uniform velocity. Got it? Similar was the task which is a gluing task. I'll show you that. So you see, robot is continuously depositing the adhesive along the path, and if at all it stops or goes with a different velocity, you will find adhesive getting deposited at a particular location. Got it? It is quite uniformly moving along. Got it? So these are a few applications. What you see are of a special kind when a robot is required to move in a Cartesian workspace at uniform velocity. So yes, now coming back to my slide, when I wanted a relation which can relate the joint rates to the end effector rates. Okay. So is there any such relation that exists? Can we find out that? So this will be known as a robot Jacobian. Okay. So this is known as a twist. This vector which is here, we will call it as twist, which is a 6 cross 1 vector. 1, 2, 3, 4, 5, 6 cross 1, and input over here will be n cross 1, whereas n is the degrees of freedom of the robot. In case of 6-DOF robot, it is 6 variable which should be input. So we are looking to find out this Jacobian matrix. So let us proceed with our standard 2R robot. What we know here is x, that is the end effector position x for this was a1 cos theta 1 plus a2 cos theta 1 plus theta 2, y is equal to a1 sin theta 1 plus a2 sin theta 1 plus theta 2. So this was the position forward kinematics. Okay, and this is the end effector position given by xy. A1, A2 are the link lengths, theta 1 and theta 2 are the joint angles. Okay, so by differentiating these two equations, what we get? We get x dot is equal to this, y dot is equal to this. Got it? So you find theta 1 dot, theta 1 dot, theta 2 dot, theta 2 dot all over here. Okay, whereas sine theta 1 is here cosine theta 1 is here, cosine theta 1 plus theta 2 is here, sine A theta 1 plus theta 2 is here. So it is containing both, that is the joint angle as well as joint rate. So this is a relation that we could obtain by differentiating the forward kinematics equations. Okay, so expanding that, I quickly can obtain this. If I can pack them together by rearranging this in matrix form, so what I see, it is x dot y dot, that is the output matrix. What it is? This is basically the twist matrix, which says velocity of the end effector along x, velocity along y is clubbed like this, and this becomes your a matrix which is of 2 cross 2 type, and you have a matrix here which is the input joint rates, and within the matrix all the joint angles are gone into sine and cosine variables which are inside. So it is a 2 cross 2 matrix. Okay, if at all you have more than 2 variables as input, so this matrix will take the shape accordingly. Output, in case of a planar robot like this, you have just x rate and y rate, so it is exactly this. So this will call it as differential motion of the end effector is related as Jacobian into differential motion of the joints. Okay, and both of them are related by Jacobian. Got it? So this is what we are looking for. Can we derive this for n degree of freedom robot? Is there a better way of doing it? Because doing it in a way like this is very difficult for, let's say, n degree of freedom robot, when you have to take derivative, take the common and get it to this kind of result. So there are various elegant approaches to do this. So we'll talk about that now. So let us do velocity analysis first. So position vector of any joint frame OI is given as OI minus 1 plus AI. What are these terms? Basically OI is the joint I vector that takes you from the reference frame O to OI, that is the ith joint which is there, and this is your link I minus 1 which is here. Okay, and you have another frame OI minus 1, so you can draw this vector now. So it is like this. So it is vector OI minus 1. So, and this is your link length vector for I minus 1th link. Okay, so that is what is written using this vector triangle like this. So OI is equal to OI minus 1 plus AI minus 1. Okay, so this is your position vector for the ith frame. Okay, now taking derivative of this. So OI dot is equal to OI minus 1 dot, that is the dot of this, that is the velocity relation, plus AI minus 1 dot. So that is rate of change of link length vector. Okay, AI minus 1 dot is equal to omega I minus 1 cross AI minus 1. How you know? You see, you have a vector which is AI. Got it? We know that magnitude of this is constant, that is the link length between the frame OI and OI minus 1. But a vector can be changed in two different ways. First, by changing its magnitude, or it can also change its direction. So two different velocity it can acquire. One along the direction which is along the axis of this vector. So this could be one velocity if A is changing in magnitude. But there is another velocity if this is rotating with an angular velocity omega. So, and AI is its magnitude. Okay. So you can take the cross product of these two vector and you can find a orthogonal vector which is like this. Got it? So this becomes your tangential velocity. This is your normal or axial velocity. This is your tangential velocity. So this is the direction of this vector, and this is due to the rotation of this link. And even if this is absent, this is always there. Okay, because your joints are moving. So if it is rotating, you see this vector. And also you have omega I is equal to omega I minus 1 plus I minus 1 omega I. What does it mean? This link, ith link, is riding upon a link which itself is rotating by some angular velocity. So whatever is the angular velocity of link which is prior to the ith link, that is the omega I minus 1, this becomes your angular velocity of the ith link. In addition to that, you also have an angular velocity which is a relative velocity. This is the relative angular velocity of ith link with respect to I minus 1th link. Let us say you have a motor which is fitted here. This will rotate this link with some angular velocity. So this becomes the angular velocity of ith link with respect to I minus 1th link. So this is your relative velocity, and this is the velocity with which the link which is prior to this is rotating, on which ith link is also rotating along with that. Okay, so this is your total angular velocity of the ith link. So using both of these, now you can write for revolute joint omega I is equal to omega I minus 1 plus this is your relative angular velocity. You know this is rotating at an angular velocity which is given by theta I dot. This is the magnitude of that. What is the direction of that? Let us say EI is a unit vector about which this link is rotating. Got it? So that may be your z axis that is placed at the joint. Got it? So this is your EI vector. So if that is an unit vector, so if you multiply that with your magnitude, so what do you get? You get omega I minus 1. Got it? Both are same. Okay. So that I have written it out here as this. Okay. So this is the first relation is your angular velocity relation, whereas the second one is your linear velocity relation that comes from here. So OI dot is the linear velocity of the ith frame, that is the frame which is over here, is equal to linear velocity on which this link itself is riding. So this is your linear velocity, and the velocity which is generated due to the angular velocity, omega I minus 1. So that is what we have seen it. Okay. So AI minus 1 dot is equal to omega I minus 1 cross AI minus 1. So this we have simply put it here. Got it? And we got to this relation. So this is quite trivial. In case of revolute joint, it is very easy to understand. In case of prismatic joint, you know there is no joint which is here which is able to rotate like this. So this is absent in case of prismatic joint. So omega I is same as that of whatever is the angular velocity of I minus 1th link. Okay. So whatever is the angular velocity of this, same will be the angular velocity for this link as well, if it is a prismatic joint. Now let us look what would be the linear velocity in that case. So linear velocity will be again similar to this. You will find OI dot is equal to OI minus 1 dot. This is the velocity of the previous link, and there are two components this time. This is due to the rotation of the link which is prior to this. So if this joint is frozen, okay, this is frozen. So what will you see? It is AI minus 1 taken cross product with omega I minus 1. So whatever is the velocity that comes at this point, so you have to add this. So this is your tangential component of the velocity that comes to OI. So this is the tangential component. Okay. This is the component which is due to the velocity on which it is itself is riding. So OI minus 1 dot. So this is the velocity. Okay. This is the velocity which is here. Apart from that, this is the tangential component, and this is your axial velocity term. In that case, you have z-axis that is along this direction. Okay, whatever is your z-axis, let us say if this is your EI in that case, and you are changing DI, you know, in DS parameter, you know it is DI, that is the offset along z-axis. That is what is changing in case of prismatic joint. So what happens? This is changing. So you have a velocity which is exactly like this. Okay. This is due to the change of DI which is along EI. Okay. And the direction of that will be along the axial direction or along the normal direction. So there are two velocities. First is due to the angular velocity with which that link is rotating, and second one is due to the rate of change of extension of that link, extension or retraction, whatever it is. So it is along the axis of that EI. Okay, that is axis of the prismatic joint. So these are the two. So sum of all the vectors, tangential, normal, and the relative velocity which it is acquiring because of the earlier joint motion. Okay, so all these together will give you the Y dot. Got it? So this is your prismatic joint. So these two relations are very, very important in order to find out frame velocity and the angular velocity of the link. This is very much utilized in order to find out Jacobian later on for n degrees of freedom robot, and also while we'll be doing energy analysis in case of dynamics later on. So let us start computing Jacobian for a general n degree of freedom serial robot. N can be 6, n can be anything. So let us first understand the structure of this link. So this is your link 1 which is attached to the frame 1, where you have an axis of rotation. Theta 1 is the angle with which it is rotating. This is attached with the frame OI, O1, okay, which forms the axis of rotation for the second link. Theta 2 is the angle. E2 is the axis about which this angle is measured. So this is basically your z-axis, which is normally, for in case of DS parameter, you know all the z-axes are placed along the axis of rotation or displacement. So exactly these are the z-axes which are there for that local frame. Okay, and then your second link comes like this, and same goes on. Okay, now you have ith link which is mounted on the frame which is OI, and you have theta I which is measured here, that is along zi axis, you know, and EI is the unit vector which is along the axis of theta I about which this link is rotating. So this vector we will call it as OI vector, that basically connects, that is the position vector of OI frame which is attached over here. This is your ith link and this is your OI which is the frame. Got it? And then you have OI plus 1 which goes here. You have EI plus 1, that is the axis of rotation about which theta I plus 1 is measured, and this link is also rotating. What is this link? This is I plus 1th link, and so on so forth till the last link, which is the nth link of link length AN. This was the link length AI. Frame here is ON, and the end effector frame will be also having a position vector. Now because I am concerned about the end effector now, so we'll attach a position vector here also, OE. So you see angular velocity 0, that is the base velocity on which whole of the robot is fitted. So that is equal to 0. So omega 0 is always equal to 0. Okay. Now you have the first axis about which first link is fitted. So you can write it as omega 1 is equal to theta 1 dot E1. Okay. E1 is somewhere over here. Got it? Somewhere over here that passes like that. And theta 1 is the angle along that vector, EI vector. Okay. So that becomes your omega 1. So all the angular velocities can be written in a similar way. So what will be the velocity omega 2? Omega 2 is because of two rotations. First, because of relative rotation, that is theta 2 dot 2, that is here. Okay. And there is one more rotation which was given to the first link. So because you have a link, you have another link. So this link, the next link, will automatically have the angular velocity with whatever is there with the link which is before to that. Got it? So this is the reason why this velocity is always a part of omega 2. Okay. So this is your omega 1 plus this relative angular velocity. So similar could be the third one. Omega 3 would be omega 2 plus theta 3 dot E3. Got it? So this will be your omega 3. And omega 2, whole of this will come here. Got it? So this is how we'll keep on adding that. So effectively what you will get, omega n, that is the last link angular velocity, will be the sum of all the angular velocities till this point. So it is summation of angular velocities of all the joint prior to I. So I am taking it till I. So whatever is the angular velocity of all the links prior to I will be giving the angular velocity to this link. So if this has omega I, so all the omegas that are here till here will be added together to give the angular velocity for this link. Got it? Not, we'll simply ignore whatever is coming next to I. This has no influence on this. Got it? Now let us talk about linear velocity. What is O1 dot? Again, because it is attached to the ground, okay, about which your link 1 is moving. So this is equal to 0. Quite trivial, very easy. Now what will be your O2 dot? So where is your O2? O2 is O1 dot plus omega 1 A1. So if this is your link length A1, so there must be a vector which connects A1. This is your A1. Omega 1 is the angular velocity of this. So this gets added on. Okay. So this is what? This is the tangential velocity vector. So this is your velocity of O1. So that is 0. You know it is attached to the ground. So there is no velocity over here. So whatever is this, so you can quickly write it as this. So it becomes simply theta 1 dot E1 cross A1. Got it? So this is equivalent to theta 1 dot E1 cross A1 2. So that we'll call it as A1. So A1 is the distance. It starts from 1 and goes till 2. So if you take it all together, so it becomes very much like this. So before we come to this point, let us discuss it in a different way. For any joint, let's say if it is 3, O3 dot will be O2 dot plus omega 2 A2. So let us say this is your third link. Okay. This is your O3 vector. So this is your O2 vector. Okay. And then you have a vector which is A2. Got it? So this is your second link. At the end you have O3. Before to that you have O2. So velocity over here will be simply O3 dot and that is the sum of O2 dot velocity over here plus whatever is the resultant of angular velocity that comes to this location. Okay, so what is that? If this is omega 2, this is A2 vector. So cross product of those two vector will be reflected over here as tangential component at location 3. This is the normal component at location 3. But because you know any normal component will be absent because this link length is not changing with time. Okay, so you have only this component, tangential component, and you have already given the base of this link 2, a velocity of v2, so that is O2 dot. So it is sum of these two vectors is the resultant velocity at this point. Got it? Now can I put it like this? So what is this O2 dot? O2 dot can simply be written as this from your earlier derivation that you have obtained. So O2 dot was because of rotation of the link 1. Okay. So you had E1, you have theta 1 dot, that is the angular velocity, Ei is the vector along the Z1, that is the first axis on which link 1 is placed. Okay, so this was there, this we have already derived. Now can I replace this omega 2 with these two? You know angular velocity for the second one will be the sum of angular velocity of first plus whatever is the joint velocity which is here. So sum of all the joint angular velocities put together till second will come here. Okay, so this is your omega 2 cross whatever is the length of this link. So this is your A2. This is your A2. Got it? So that comes here. So now I will simply rearrange that. Okay. I have put together theta 1 dot E1, that is there here, that is here, together and cross product with A1 plus A2 that goes to this bracket, and the last term which is remaining is this that comes here. But it's simply rearranging that. Okay. So now you got what? So what is this? Theta 1 dot E1, that is as it is, A1 plus A2. What is that? So this is your A1 vector. This is your A2 vector. So sum of this basically came here. Sum of those two. So it is what? It is A1 to 3. So from here, this is 2, this is 3. So this is the final vector that is obtained. So A1 to 3. It takes you from 1 to 3. So that is the vector which is here. This remains as it is. I have simply put this as A2 as 2 to 3. It takes you from 2 to 3 points. Okay, so this is it. This is nothing but A2. Got it? So this is your O3 dot. Now let us come back to our original slide. So what you see here, O2 was arranged in a similar way. O3 we have just derived. So what is effectively On? If you take it further till n, you will see it is theta 1 dot E1 cross 1 to n. So 1, 2, 3, 4 till n. Okay, we have to reach till here. So this is your vector. So this is your first term. The second term is from here till nth frame. Okay, if it is taken till n, it has to be till n. Okay, 2 to n. Similarly, 3 to n, 4 to n. Finally, you will get n minus 1 to n. So you have this vector. You must be having a link which is prior to this. That becomes your n minus 1 frame. Okay, to n. This is the frame. Okay, so that also will come. So when you have to consider till n, you will see this particular equation. So what effectively you understand here, So I'll just draw it once again. I'll make you understand now. So let us say you have a robot which is a serial chain robot which is connected like this. There are n number of links which are there. There is n minus 1. Finally, n, even you have an end effector which is here. What if this is attached to a frame? So this has some velocity. Okay, let us say you have frozen all these. You have frozen all these. Got it? All the joints you have frozen. So what will you see? This, if this is your angular velocity 1, okay, so you have a distance which is like this, a1 n. If this is your nth frame, okay, nth frame, so 1 to n, so this is the distance. So you will see a velocity arising due to omega 1 will be omega 1 cross a1 n. What if a1 n? So that is the velocity component due to this angular velocity. Now let us do the second one. Now I'll take this motion omega 2. Okay. Again you consider all these as frozen ones. Okay. So omega 2, because it is rotating. Okay. So from a distance from here till end will be a2n. Okay. So this is the vector of nth frame from second. This is your angular velocity. So component due to this will be omega 2 cross a2n. Is it not? a2n. So you have two velocities. First, something like this you will see, that is normal to this, and the next one is normal to this. Okay, second one, and then you may be having yet another one. Let me do once more. Okay, so this link is also moving. Omega 3, you have third velocity vector, that is a3n. Third component will be omega 3 cross a3, and that comes here again perpendicular to that. Okay, so whatever is the nth frame velocity you see, it has components of all these components. So all the omegas have a contribution to the velocity which is seen here. Okay. So this is what is reflected over here. This is your first term, this is your second term, this is your third term, so on so forth till the nth term, n minus 1th term. Got it? So all these will have effect at the end. Okay. So what is this? This is just the distance what we have just understood now. It connects I to the jth frame. So these are all the linked lengths which are added together to reach till here. So this is there. So this is explained here. Omega E is equal to omega n. You know, last frame which is fitted at the end effector frame. So that is fitted at the nth link. So omega n will be equal to omega E. But in this case, velocity, linear velocity will be velocity over here plus omega n, which is here, omega n times of a n e. So n to e you have a vector a n e. So this vector comes here. Okay. So that will give you the resultant velocity. Just like the previous one, this is your velocity. So now both the equations, the angular velocity equation and the end effector velocity component can be written like this, as we have just derived. So angular velocity at the end will be sum of angular velocities. Velocity of the end effector will be theta 1 dot E1 times A1E, similarly A2E, an minus 1e, ane. So all the contributions will be added together till the end effector. You reach till this. So these are the two equations. Arranging together, you can write it as omega, that is the angular velocity and the linear velocity like this in the matrix form. And the top one will have These are EI vector, E1, E2, E3. What are these? Basically, these are Z axes that we normally place at the joint. Got it? So these are nothing but those axes. Okay. And what are these? These are cross products that are this one, this one, this one, all taken, extracted out. Finally, you have joint angular velocity vector, which is here. So this is your final derivation that you were expecting. So this relates the end effector rates to the joint rate. So this is your Jacobian. Got it? So your Jacobian has two components now. First is your angular velocity component, these, and the bottom one, this will be known as the linear velocity component. So you have J omega and JV. So this is basically of the dimension 6 cross n. Why, this is what? These are all vectors of 3 cross 1. Okay. So if it is E1, can be 0, 0, 1, maybe some other 3 terms like that. So this is 3, and similarly this is 3 column of 3. So 3, 3, it is 6, and n dimension robot. So it is 1, 2 till n. N degrees of freedom robot. So it is till n. Got it? So this is the dimension of Jacobian. Okay. So in case of revolute joint, it is ith term look like this, EI, EI cross AIE. So ith term will look like this. Any particular one you can find it out. And in case of revolute joint, you see there is no angular velocity component that will go. Okay. So that is making this term 0. And velocity was only, it is not the tangential one, it was along the direction of the axis. So it makes this like this in case of prismatic joint. Got it? So this is the general expression of Jacobian that you need to remember. We'll use this expression in the next class and move ahead further. So we'll do Jacobian of 2R manipulator, 2 degrees of freedom planar manipulator, exactly the one that we did. Simply by taking differential, we'll use this particular relation and we'll try to find out the Jacobian. Okay. We'll see why Jacobian inverse is required and how to go for it. We'll understand what is singularity, and we'll see acceleration analysis also. That's all for today. Thanks a lot.